the MFPA's Next Generation seminar series is a networking event for early career scholars, juniors, modelers, and epidemiologists working on or interested in the mathematical modeling of infectious diseases and other threats to public health. Bienvenue à tous. La série de séminaires MFPA's Next Generation est un événement pour les chercheurs en début de carrière, les modélisateurs juniors, les épidémiologistes travaillant intéressés par la modélisation mathématique des maladies infectieuses et d'autres menaces pour la santé publique. First of all, we wish to acknowledge this land on which the Fields Institute operates for thousands of years. It has been the traditional land of the Huron-Wendat, the Seneca, the Mississaugas of the Credit. Today, this meeting place is still the home to many indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. Premièrement, nous souhaitons reconnaître cette terre sur laquelle l'Institut Fields opère. Depuis des milliers d'années, c'est la terre traditionnelle des Huron-Wendat, des Sénèques, des Mississaugas. Aujourd'hui, ce lieu de rencontre abrite encore de nombreux peuples autochtones de toute Turtle Island et nous sommes reconnaissants d'avoir l'opportunité de travailler sur cette terre. Our guest today is our Professor David Buckridge and Nathan Duarte. David is a professor in School of Population and Global Health at McGill University in Montreal, where he directs the surveillance lab for population health surveillance. And he is also the chief digital health officer at McGill University Health Center, where he directs strategy on digital transformation and analytics. And he is associate member with the Montreal Institute for Learning Algorithms. His research and practice focus on the informatics of health surveillance and disease control, and he holds a Canada Research Chair, Tier 1, in health informatics and data science. Today's speakers also is Nathan, is now pursuing a master degree of science in electrical engineering at McGill Faculty of Engineering, and he was a biomedical engineering student at the University of Waterloo. Nos invités aujourd'hui sont le professeur David Buckridge et Nathan Duarte. David est un professeur à l'École de santé des populations de santé mondiale à l'Université de McGill à Montréal, où il dirige le laboratoire de surveillance de la santé des populations. Il est également directeur de la santé numérique en centre universitaire de santé McGill. Il dirige la stratégie de transformation digitale et analyse. Il est membre associé de l'Institut d'apprentissage des algorithmes de Montréal. Ses recherches et sa pratique portent sur l'information, la surveillance de la santé et du contrôle des maladies, des chaires de recherche Canada, niveau 1, en informatique, de la santé en sciences des données. Nathan poursuit actuellement une maîtrise en sciences de génie électrique à la faculté d'ingénierie de McGill. Il est étudiant en génie biomédical à l'Université de Waterloo. Their talk will be on statistical modeling of the incidence of SARS-CoV-2 infection from wastewater and serological data. Leur présentation portera sur modélisation statistique de l'incidence d'infection par SARS-CoV-2 à partir des eaux usées et des données sérologiques. Nathan, the floor is yours. Thank you very much.
Thanks for that kind intro. So we can jump straight in. Today we'll be talking about joint statistical modeling of the incidence of infection using wastewater surveillance data from a couple of Canadian cities, as well as serological data collected by Canadian Blood Services. You'll have to pardon me as well if I might take a sip of water. I'm just recovering from a stretch of COVID. But without further ado, we'll jump straight in. So I'll start with motivating why we would even want to, look at these two epidemiological signals together. So there's a lot of different ways we can actually try and recover the incidence of infection, which is simply how many infections of COVID happened each day historically. So previously, we were able to evaluate these signals along several important dimensions, including representativeness. So how much bias there is in this signal compared to other signals. Do they give us an accurate picture of the population? Sensitivity, which is what percent of infections are we actually capturing? Timeliness, which is how soon after an infection occurs are we able to actually detect that infection has occurred? Positive predictive value, which is the percent of the detections that occur that are actually true infections. So this has to do with whether we're getting a lot of false positives or not, or if we're efficiently targeting a population. And then finally, scientific maturity, which is how well do we understand this modality of an epidemiological signal. There's a few other dimensions we can evaluate each of these signals across when thinking about what's going to help us track the incidence of infection. Some of them include flexibility, cost, public acceptability, but we'll focus on some of these core 5 that I've outlined first. So lab confirmed cases, PCR case counts, these are what has been used throughout most of the pandemic to try and understand how many people are being infected over time. But there's a few issues that have come up over time with these signals. They're not super representative insofar as we miss a lot of asymptomatic infections. With low testing capacity, tests have been prioritized towards symptomatic and severe disease. As well, the timeliness is not great because usually it's contact tracing and symptoms that prompt someone to even go seek a PCR test in the first place. So overall, these have been a standard backbone of clinical practice and outbreak management, but they've not been the greatest signal with respect to surveying and getting a complete picture of what is going on. On the other hand, seroprevalence, so that is the fraction of the population that has antibodies against COVID. Seroprevalence has been a much more reliable indicator insofar as with appropriate sampling, we can get a very good representation of the population. Further, things like symptoms, things like access to tests don't really have a burden on whether or not you develop antibodies. So these are very sensitive types of tests and types of studies that go on, because the theory is that everyone that gets infected will, for the most part, develop antibodies. The downside of seroprevalence studies is that they're not very timely. So it takes a couple of weeks after you're infected to even develop an antibody response. And then from there, several weeks to actually have your blood collected and for those results to be compiled and made publicly available. So that's the issue with seroprevalence. And people have tried to combine these two signals together in the past, taking the advantages, what they are of lab confirmed cases being a bit more timely and seroprevalence being a bit more representative, and using the relationship between the two to correct the signal from lab confirmed cases. So for example, if we know these lab confirmed cases systemically underestimate how many infections occur, maybe we'll be able to multiply them by a factor or correct them for bias to get a better understanding. So this was a common strategy that was used for most of the pandemic. But when the Omicron wave occurred and when rapid tests became available and we faced severe test supply issues, changes in policies, changing in test seeking behavior really caused us to look at other ways beyond looking at lab confirmed cases of understanding how can we triangulate how many infections are going on in the population, how many people have developed antibodies, et cetera. Effectively, the relationship and the reliability of lab confirmed cases broke down from that point on and are being reported less and less frequently. So we need an alternative kind of strategy for understanding what is going on. So we have several options. Hospitalizations and deaths are a common option that have been used throughout the pandemic. They have high positive predictive value insofar as every hospitalization and every death, we know this was a case of COVID. The issue is that not everyone in the population is going to be at equal risk of these outcomes, so the representativeness is less high. And also, these are less timely insofar as someone first has to go to hospital or die. And then this has to be reported for all of this to show up and for it to be useful in our statistical modeling. So these aren't the best candidates for understanding how many infections are going on. On the other hand, there are some exciting new technologies with apps that collect symptoms, smartwatches that collect physiological signals, as well as online queries like Google flu trends, Twitter trends, that could have some use, but these are simply just too new and uncharacterized in terms of their bias and what they're actually telling us, to be super useful in this regard. So what that leaves us with on this chart is the viral concentration of SARS-CoV-2 in wastewater. And this is an exciting sort of signal. It's been around. People have been looking at viral concentration of different particles in wastewater for years at this point, but it really blew up in popularity with COVID because, of its representativeness, its sensitivity and timeliness. So as just a few examples of how the viral concentration of COVID has been used in the past, by sampling from sewage plants and measuring how much virus is in there, we've been able to detect different variants weeks before they've been detected by conventional measures of genomic surveillance. We've been able to detect rises in the viral concentration that precedes other indicators to indicate that there's an outbreak going on. And in general, this has been super helpful already, and a much more useful measure in that we don't really need to rely on people going and seeking tests or being tested. The unfortunate part of this is that the actual science behind wastewater measurements of SARS-CoV-2 are still new. So every municipality, for example, has a different strategy for detecting how much virus is in the wastewater. And I'll just walk through kind of some of the challenges behind relating the concentration of virus in the wastewater to the actual number of infections. We can pretty clearly break this along the data path that follows. So once someone's infected, they shed the virus. However, even then, at the viral shedding phase, the amount can vary based on how long it's been since you've been exposed, your age, how severe your disease is, the variant, and as well the location. Some people could be located further away from a plant. Some people could be commuting and shedding in a different sewage treatment area. There's some other challenges once the virus actually gets into the wastewater system. For example, there's delays between when the virus is shed in someone's house and when it gets to the actual treatment plant. The concentration can change with heavy rain or with temperature. There's sedimentation and other issues that occur. And then finally, as I mentioned, every municipality has its own protocol for sampling the sewage, for extracting the actual concentration, and then for normalizing it. So this makes it very difficult to use the wastewater concentration of SARS-CoV-2 in a quantitative way beyond just looking at trends. It's very difficult to relate this concentration to an actual number of infections that historically occurred. So that's the challenge at hand. That's what we're trying to understand. Can we use this signal in conjunction with seroprevalence, which has been a much more stable and representative indicator, and get the benefits of the timeliness of wastewater and the representativeness of seroprevalence to understand together what is going on with respect to the incidence of infection? So we really have two questions here. The first is, do wastewater data improve our ability to retrospectively understand the incidence of infection from serological data? So what that means is, can we use these two signals together and triangulate historically how many infections occurred day over day or week over week? And then the second use case of this is, can wastewater and serological data be modeled to nowcast seroprevalence? So as I mentioned, wastewater has the advantage of being very timely, whereas seroprevalence is very representative, but less timely. So can we use the fact that we have real-time estimates of wastewater to kind of figure out, if we had real-time estimates of seroprevalence, what would they be? And that would give us better understanding of population protection, exposure, et cetera. So we'll explore these two questions from a modeling approach throughout this talk, and we'll see if there's promise behind using these two signals together to understand the incidence of infection. So this is the data we're actually looking at. I'm showing here seroprevalence, in particular anti-N seroprevalence over time in 8 wastewater treatment plants in Canada. There's Edmonton, Halifax, Toronto, Vancouver, and 2 Winnipeg plants as well. I'm showing on the x-axis time from around February 2021, which is when wastewater data started to become available, all the way until around May 2022, which is the time in which we'll consider data for this analysis. You'll notice that I'm showing in the size of the circle the sample of the seroprevalence estimate here. So really, this has you can see disparities already between different plants. Some are relatively well sampled with samples in the size of hundreds, whereas others have smaller ones, sometimes even less than 100. So this is a challenge that we'll have to think about and account for in constructing our model. But in general, we have good coverage of seroprevalence data, blood connected by Canadian Blood Services, and just to recap once again, what this tells us is the fraction of people that have antibodies as a result of prior infection. On the other hand, the wastewater data that we're dealing with looks like this. So these are collected again by each of these municipalities. What I'm showing in the size of the circle here is how many days a week people are collecting this data. So it's not all the time. In some municipalities, people are only collecting a wastewater sample twice a week, 3 times a week, whereas in others, there's relatively more granularity with respect to sampling. But in general, we see strong trends in the wastewater data. We see different peaks that represent different waves of infection. And on the y-axis, I'm just showing the viral concentration. So this doesn't actually mean anything in terms of the number of infections that occurred, but it tells us what the concentration is in these plants. So we can use some principles behind the actual epidemiological signals to generate a model. So we structured our model as follows. On the bottom, you can think about infections as a time series, a latent time series that's unobserved, and this is what we're trying to triangulate. And we've structured a model such that these 2 other signals, so this seroprevalence and the wastewater concentration, are generated from this latent unobserved process. We observe both of these, and how we observe them will describe how we construct our model. So I'll walk through some of the underpinnings of this model in a sec. We first structure the underlying unobserved infections process as a multiplicative autoregressive process. Really what that means is infections on 1 week are simply multiplied by a factor, either greater than 1 or less than 1, to get to infections on the next week. And this just reflects, we're trying to capture the exponential growth and decay nature of this process. So the first process that's generated from this underlying infections process is the seroprevalence process, which we observe. So there's 3 steps here. The first is to recognize that an infection on a given day will not remain seropositive forever. And there's several reasons as to why this is. The simple answer is that it's natural once you're infected for your antibodies to spike once you've developed an immunity to the infection, and then over the coming months following that to decay as you lose that antibody response. And we're talking about binding antibodies, to be clear, but there's a clear profile over time of the decay in how likely someone is to remain seropositive weeks after they've been infected. So the way we account for this is by simply multiplying backwards. So if a seroprevalence study is conducted on a given day, we multiply backwards the probability that 2 weeks ago, everyone that was infected has a certain probability of still being detected with antibodies. 30 weeks ago, they have an even less probability of being detected with antibodies. So ultimately, what we're trying to do is we're trying to take what infections have occurred and understand how many of those infections do we still expect to remain seropositive and have antibodies. The next step is to actually convert that number of still seropositive infections to the percent of people still seropositive. And this is a subtle distinction because more infections could have happened than people with an antibody response. And that's simply explained by the possibility of a reinfection. So we can treat this as a simple sampling with replacement problem, where the assumption is that a reinfection occurs independently of past infection. And obviously, this is a strong assumption. We have some rationale as to why we put that in. But effectively, what we're doing here is we're converting how many infections happened in the past to how many people we expect to still have an antibody response. And then finally, we use a binomial term at the very end of this Bayesian model for seroprevalence to just account for variation due to sample size. As I noted, the sampling is different over time and across plants. So this was an important addition as well to get the final seroprevalence. On the other hand, we can also structure a process of generating a wastewater signal from infections. So we've developed a very simple model actually where we only have one multiplicative factor, that's this beta W term. So you can think about it as the infections a week prior are multiplied by this beta W term. So that accounts for any dilutions, that accounts for any efficiency loss from the extraction process, that accounts for really anything that could occur that's constant over time and varies by plant. So once you multiply those infections by that scaling term, which is a kind of catch-all parameter, you can then put it into a normal and then have an error term as well to reflect plant-specific time invariant measurement error. And that's how we arrive at the concentration in wastewater through this model. In the future, we could also consider time varying factors like temperature and precipitation, and it would be as simple as adding a time varying coefficient here, but we haven't done that. We've tried to keep our model as simple as possible for now. And in terms of the priors, we've just kept very uninformative priors because we're not, as I mentioned, certain as to how the concentration relates to the number of infections. So altogether, we have this model. We've structured it as a sort of unobserved component, which is the infections, and an observed set of signals that we can then use to fit the model. And we can now start answering questions with this model and with the data that we have. So the first question we'll look at is whether we can use these data to retrospectively understand how many infections occurred. So I'm showing here as a baseline, what happens when we fit our model just to seroprevalence data? It's a good question. I'll just go back really briefly and answer this question. Copies per ml is bounded by 0, yes, but we take the log of it. So we're modeling log wastewater. And usually we don't see 0 copies per ml. But anyway, so what I'll start to show is a baseline. We want to get a baseline where we just use seroprevalence data to fit this model, and then we'll compare it to a model with both seroprevalence and wastewater to see what additions in inference does wastewater actually provide us. So what I'm showing here on this top plot in purple is the number of infections that we come out from our model with per week, and these are unobserved once again. And then this bottom plot is showing the seroprevalence, and I'm overlaying observed data to show that there is a good model fit. And I'm also highlighting in gray bars the first Omicron wave, which will center some of our analysis on. So we see in this Toronto plant, I'll use 3 plants as an example, not the full 8. We can see, clear spikes, clear trends in infections that reflects the first Omicron wave and future waves. We see very large confidence intervals at the end. I will just say that these are more effects of the actual model and the actual clipping of the time series more than they are actual uncertainty in the data. So if we hypothetically fit a longer time span, we wouldn't have this large confidence interval at the very end. Nevertheless, though, it's still undesirable to have that degree of confidence or that lack of confidence rather so close to real time. So this is what we get when we look at seroprevalence only as a baseline. This is how the Vancouver wastewater treatment plant looks. So different profile as expected. They had a different epidemiological outbreak, but nevertheless, this is what our baseline looks like. And again, we see really large confidence intervals at the end. And then finally, the third example plant I'll be using throughout is Halifax. Halifax, again, a small wave and then a large wave. So once again, a different profile in the Omicron era. And things are relatively flat in all three plants prior, and that just reflects the lack of, large infections. And we see that's not an artifact of any sort. Indeed, the seroprevalence was very low, suggesting that there really weren't that many infections that led to an antibody response or immunity prior to around November 2021. But now, what happens when we take this baseline and we compare it to fitting the model with wastewater data? So I've simply added another row, which shows the log concentration of wastewater over time in this period. And we see again, the model achieved good fit to this. The model diagnostics were all, passing criteria. And we see again, very similar trends, first wave, second wave in Toronto. The big difference that we see is that there's an added precision. The confidence intervals, especially when we have big waves and such, are much narrower, especially towards the end. And what this could suggest is that wastewater adds a degree of precision by when it's combined with seroprevalence in inferring how many infections occurred over time. For Vancouver, the case is similar, although we do see again a bit of a ballooning in the confidence intervals towards the end. But nevertheless, we see a clear trend of first wave, second wave. And then finally, with Halifax, again, the same trend. But now what I'm going to do is I'm going to double down and hone in on this region, the first Omicron wave, and we'll do some side-by-side comparisons between having a model that's fit only to seroprevalence and having a model that's fit to seroprevalence and wastewater data. Just before that, I wanted to show how the posteriors of the wastewater samples of the wastewater model fit to each region. We see it's well informed by data. This uninformed of prior has converged to relatively narrow and consistent posteriors across plants, and same with the error term as well. So our model has indeed learned from the wastewater data and is being informed by it. So when we put the two kind of versions side by side, without wastewater, so only with seroprevalence, and then with both of them on the bottom, we see very, very similar patterns. There's slight differences in the magnitude of the waves. There's slight differences in the precision, so the confidence intervals, especially towards the end. But in general, from Toronto to Vancouver, Vancouver, for example, the difference in confidence is clearly noted. We get much more precise estimates of the incidence of infection with wastewater, and then the same with Halifax. But I'm going to summarize this in this plot, which looks at just that first Omicron wave. I'm simply showing here, again, without wastewater in pink and with wastewater in green, what the total number of infections in that period, that first Omicron wave period actually was. And we see, like, as we saw qualitatively, even quantitatively, there isn't that much of a difference between how many infections we've inferred to have occurred. There are, there instances of increased precision, for example, with Ashbridges Bay here, especially, for example, in South End, Winnipeg. But in general, the effects of wastewater have not been too dramatic. Just added precision and slight more, a bit of bias that hopefully is converging towards the true number of infections. We can switch though to answering the second question that we wanted to look at, which is, can wastewater and serological data be jointly modeled to nowcast seroprevalence? So just to talk a bit more about the motivation for this, I've put an excerpt image from one of the papers that our group has put out studying the timing of sero surveys and the results relative to when the sampling actually occurred. And we see that there's really large delays, basically, and we're stratifying by publication venue. On the x-axis, we have the time to publication. On the y-axis, we have the probability that a piece of work is published. And we see that it can take hundreds of days to be published and for seroprevalence results to be available. So as useful as we've just demonstrated seroprevalence is as an indicator for understanding and triangulating the incidence of infection, these aren't always available in real time. So we need to see if there's a way that we can sort of make up for this with wastewater, and whether wastewater can help us. So we structured the following experiment to see and explore this use case. What we were doing previously is we were fitting in the entire time series from February 2021 to February 2022, or May 2022 rather, of seroprevalence data and of wastewater, and we want to infer the unobserved instance of infection. But here, what we're also doing is we're not feeding in the last 8 weeks of seroprevalence data, and 8 weeks comes closer to the lag that we have in seroprevalence in Canada. But we're not feeding in these most recent 8 weeks of seroprevalence data. We're only feeding in wastewater and seroprevalence up to that point. And we're trying to see, not only can we recover the incidence of infection, but can we also understand what seroprevalence would have been if we were able to have real-time estimates of seroprevalence. And again, this is very useful, not just for triangulating the incidence of infection, but seroprevalence also tells us a lot about population level protection and immunity and other such factors. So this is a valuable use case if we can actually make it work. So I'll show you the results for these same three treatment plants. The only difference in these plots, I'm plotting the same thing on the top, infections, then seroprevalence, and then wastewater on the bottom. But here with this gray line, I'm just highlighting visually when we stopped feeding in seroprevalence data. So these X's, we never fed into the model. They're unobserved by the model. But in pink, the confidence intervals are what the model has kind of predicted should occur with seroprevalence at that time. So we can actually see that in the context of the first Omicron wave, which is what I'm showing towards the end of this plot, we are actually able to recover this uptick in seroprevalence because there was also a spike in wastewater at this time. So this is very helpful and very useful for us to know that we can correlate spikes in wastewater using the historical relationship between wastewater and seroprevalence to understand how can seroprevalence potentially change when it's not observed. So the same is true for Vancouver. We were able to capture the trend in seroprevalence that we saw, and obviously, it diverges the further out we go in the future, suggesting that the wastewater relationship is time varying. But we can again capture this first wave of Omicron. And again, the same is true for Halifax, but with admittedly larger confidence intervals. So everything fits in. We capture all the unobserved data within the confidence intervals, but with less certainty. So all in all, we found until around February 2022 that we're actually able to make this public health use case work with wastewater data. And that was very reassuring. But what if something surprising happened when we tried to do this until a future date? So we repeated the experiment. Sorry, just before I talk about that, I'll also share quantitatively the results of this experiment. So just to talk a bit more about what we found, here I'm simply showing in green the forecast without seroprevalence data. So that's what you see in this pink chart, and in purple after this gray line. And then I'm comparing it to the same experiment where we did provide all of the seroprevalence data. We see that the number of infections that we capture is actually relatively consistent. It's systemically underestimated, but the median, the median number of infections that we would have predicted in that time had we had all of the data available typically falls within the confidence intervals without the seroprevalence data. So in addition to what I was saying about being able to capture the trend in seroprevalence, we can also reliably, until this point, until around February 2022, capture the incidence of infection as well from wastewater, although it's, again, systemically underestimated. But as I was saying earlier, we noticed a shift in behavior of this forecasting once we went past February 2022. What happened was we saw additional waves, as I've shown in previous plots, of infections that should have occurred. And this is again reflected in the true trend in seroprevalence. There were many more infections that led to this, that led to an ongoing increase in seroprevalence. But when we extend this forecasting experiment to May 2022, we're actually not able to capture that anymore. Really, what we're saying here is that the spike in wastewater that occurred during the first Omicron wave and allowed us to forecast this initial increase in seroprevalence, we didn't observe a wave of similar magnitude in wastewater in future waves of infections. And that suggests overall that past around March 2022, the relationship that had previously held has changed. And the task at hand now is figuring out why that is. We can look at other wastewater plants too. I was just showing Toronto, but if we look at Vancouver, the same issue occurs where the trend in wastewater is not capturing this continued rise in infections, and that makes it difficult to forecast in this time era. In Halifax, it does appear a little bit better. We are able to recover seroprevalence at the very least, but I think I would say this is still a bit faulty insofar as seroprevalence towards the very end rises rapidly, but this rapid rise is not captured in wastewater and is not captured in our forecast of seroprevalence. So this is something that was concerning to us and that is still under investigation, which is why are we able to forecast with a stable relationship between wastewater and seroprevalence up till around the first wave of Omicron and capture that wave pretty well. But onward into 2022, that relationship appears to break down. So to visualize this, I'm showing again the difference in the number of infections that we forecast in that 8-week period. Without seroprevalence, again, in green, and with seroprevalence in pink. And the underestimation is even greater across all of the plants that we're considering. So once again, this is simply because we didn't see as large of a spike in wastewater. And this is because the relationship between seroprevalence and wastewater that we have learned through our model until the point of forecasting simply stopped holding once we entered 2022. So this is an open question for this use case. I think if we really wanted to use wastewater and the past relationship, we'd have to really rethink kind of how are we structuring our model and what is going into changing that relationship. So I'll end off here with a couple of final points on what we've learned and what we've achieved through this modeling exercise. The first is that joint analysis of wastewater and serology data does have potential to improve the incidence of infection, either by shifting it a little bit or by adding precision. Wastewater does add value to seroprevalence data. And there is a theoretical foundation for supporting real-time estimates of seroprevalence, as we've shown up to a certain point. However, for these use cases, in particular for the real-time use case, for them to be truly trustworthy and robust and reliable into the future, we need to understand what drove changes in the relationship between these two signals. We need to update our models accordingly for this to really be useful to public health. And there's a few hypotheses we have as to why this change in relationship occurred. The first is that potentially our assumptions around the waning of antibody levels. So, the probability that someone remains seropositive, and about reinfection, perhaps those changed over time. It's also possible that adding time varying covariates to our model and making our model more complex. It's a very simple model right now, but perhaps adding these covariates could have predictive power. And then finally, it's always possible that the viral shedding per person just changed as a result of the severity of infection or additional vaccinations being available. So these are all things that we intend to look at to flesh out these use cases. But overall, our very simple model has shown that there's potential to use and combine these two data sets in a way that addresses key public health questions, and in a way that makes up for shortcomings in previous epidemiological indicators. So with that, I'll end off. Thank you for your time. I noticed there's a few questions in the chat, so maybe I can start by answering those, and then happy to answer and discuss about anything else.
Thank you very much, Nathan. Is there any question? I think there is a question by Martin.
Yeah, so
ignore one at the top one because I misread a graph. But the bottom one you kind of covered. I was basically saying, you mentioned temperature. You went off a bit in the warmer seasons, sort of with the second spike, which was in a warmer temperature climate. And I was just wondering if it was possible that the CPA, the particles per milliliter, or whatever you were actually measuring in the wastewater, could have actually been digested, simply because of the fact that ongoing biological processes, warmer temperature, therefore stuff could be being digested.
Yeah, no, it's very possible. I think it's one of the immediate next experiments we'd like to try. I think the reason we didn't try it already is because we kind of had an entire year of data to learn the model with already. So we kind of figured that we capture the variation in these time varying factors like precipitation and temperature implicitly, but obviously, this is an open area, and we should certainly try it as a possible explanation. There could be year to year variation that we didn't see. So.
Does it answer your question, Martin?
Yeah.
Thank you. So, is there any other question? So I was wondering, does the age of the population impact the concentration for COVID viral load in the wastewater?
Yeah, we think it would, because indirectly age has an impact on disease severity, and disease severity is something that guides the extent and the duration of viral shedding. So the age profile of a population we think would be impactful. We kind of have tried to address this issue by having plant-specific factors. So that multiplicative factor, as well as the plant-specific error term, these kind of hopefully would account for all of this together, and anything else that varies by region but is constant over time.
And for the time to get the data from the wastewater and for the blood samples, how does it take, and to get this values for the concentration?
So the concentration of wastewater has been relatively real time. I would say like within a week. I've seen them be available. Wastewater trends are what guide kind of policymakers day to day in a lot of cities, understanding if it's rising or falling. So it's very important for those to be real time. For seroprevalence, it really varies, as I was mentioning, by publication venue and by country. But in Canada, we have a program with Canadian Blood Services, and typically that's been around 2 months after the sample has been collected that we've been able to get access to the data.
Is there any other question?
I was just wondering, I've already had one question, so has anybody got any other before I go?
Well, you can go.
Okay. Yeah, I was just wondering, you're talking about bringing in temperature and precipitation to improve the fit of your models. Have you considered other factors, say mobility or whatever else that could possibly could be put in, or even opening and closing of schools?
Yeah, it's a good point. Another factor that we've considered is the time varying disease severity, if you will. Now, this isn't something that's like observed or captured directly, but other models exist that have been trying to model the breakdown of severity of infection over time. And from there, we can get kind of maybe a reading of what percent of infections have been severe versus not severe as a time series.
So just say hospitalized or ICU cases.
Potentially. I think, yeah, that could be a proxy, but what that would do is kind of allow us to explore this third hypothesis around viral shedding per infection. But we haven't considered things like mobility or lockdown presence or absence, simply because we've tried to kind of create this model very mechanistically with direct hypotheses as to what any given parameter would add or take away. But definitely something to try.
Okay, thank you. Is there any other question?
Yeah, I have a question.
Yeah.
My name is Katya. That was super interesting. Thank you. So how do you think that they're going to use this in public health, and how would the scientific community use this? Like concretely, what would they do with that knowledge that, we're expecting elevated rates of infection in the coming 8 weeks?
Well, I think several things. So on one hand, there's the implications for immunity, and if we understand that immunity is forecasted to rise in these 8 weeks based on wastewater and what that tells us about infections, we can be better prepared for scenarios like school openings or other instances where it's not certain whether there's going to be an outbreak when people get together, for example. That's just one kind of example I made up right now, but I think the implications on protection are pretty important to understand. In terms of the actual number of infections, usually that's more to do with understanding disparities between populations and regions. So for example, depending on how granularly the wastewater is captured and sampled, we could understand, this neighborhood's been affected rather much more severely than other ones. And perhaps, I think from there, you can do a lot of triangulation and retrospective analysis. For example, if we know that there have been more infections in neighborhood A versus B, but that hasn't come across in our other indicators, that could signal to us there's a problem that we should be investigating, in other surveillance systems or in other, interventions that are ongoing. So I think as to how people exactly use the incidence of infection or seroprevalence, there's many different answers to that, but I think getting reliable, timely estimates of these parameters has been pretty important.
Yeah. Yeah, that's super interesting. And have they kind of zeroed in a bit more on what the immune response that's related to protection? Like you use the N.
Yeah.
Do you know anything more about, I think they said spike is long lasting, so it's probably not the best choice, but do you know anything more about that?
Yeah, so the immune response is being very well studied by the immunity task force that we do this work with, and in general groups around the world are studying kind of concepts like hybrid immunity and what protection vaccination provides as compared to infection and such. But I would just comment that the reason that we use anti-N seroprevalence in this case is because the vaccines that we have in Canada only elicit a spike response, whereas infection elicits a spike response and a nucleocapsid response. So if we were to measure anti-spike seroprevalence and consider that in our analysis, we'd have to include the additional complexity of where that spike antibody came from. Did it come from vaccination or did it come from an infection? Whereas by measuring and focusing on NT and seroprevalence right now, we can be certain that this has come from an infection that this person has previously had.
Okay, yeah, that's a really good point. Thank you.
Thank you very much. Is there any other question? Okay, I think with that, now we are at the end of our talk. Thank you very much, Nathan, for this wonderful talk. And before